Good afternoon, everyone. Welcome here in the Blauwe Zaal for this Studium Generale lunch lecture. In the coming hour, because this is an extended program, we're discussing a topic that concerns all of us because it is all around us, chemicals. It was just a few weeks ago, I don't know if some of you saw this in the news, that there was a new publication in Nature on microplastics. And it calculated that the amount of microplastics in our brain adds up to the size of an actual plastic spoon. That doesn't sound too good, does it? But how bad is it? There's also a lot of discussion, for example, about PFAS, pesticides, and various other chemicals that we are exposed to on a daily basis. How much risk do these actually pose to our health? And when is something a real risk, and when is it an unfounded fear? Our speaker of today, Martin van der Berg, advocates for taking a nuanced look at the toxicity of chemicals in our environment. He is an emeritus professor of toxicology at Utrecht University. He's currently very active internationally as a consultant. He was recently appointed to a special advisory panel of the WHO. He is here to tell us more about properly understanding toxicological risks. So please welcome Martin van den Berg.
Good afternoon. I'm Martin van den Berg. I am still involved, although being emeritus, with a lot of toxicological studies and especially risk assessment from chemicals, mostly in international contexts like the World Health Organization and the International Agency for Cancer Research. I have to apologize a little bit because, like many others in the Netherlands, I had some flu and it's still in my throat. So excuse me if I have to cough now and then, but let's hope I'll manage it without doing that. I'm also editor and Elsevier editor-in-chief from 2 journals, and interesting, one of them is related to the regulatory aspects between, on the one hand, government agencies, and on the other hand, industry. Regulatory Toxin Farm, and the other one is relatively new journal, Current Opinion in Toxicology. Well, the word says it already, Current Opinion, and we founded it about 6-7 years ago, and it's already in the 95% percentile. They're up in the field of toxicology. What I'm going to talk to today is, first of all, I'm going to give you a kind of short introduction how we do it, because toxicologists don't wake up in the morning and suddenly think, oh, I think this is dangerous or not. There is a lot behind it, and right now, being at a technical university, it's the first time that I'm doing this for a technical university. I assume that not all of you are aware of the whole procedure, the whole systematic approach which is behind it. So that's what I'm going to talk about first. Then I'll take 2 topics which are, let's say, timely right now. And unfortunately, I didn't take plastics, microplastics, but I take PFAS, and I take pesticides, especially possible risk for neurodegenerative diseases like Parkinson or neurodevelopmental aspects in children. Okay, so how do we determine risk in toxicology, and how do we tell you that something is safe or not? This is probably my most important job. Of course, it's very nice in the laboratory when I was still appointed at Utrecht to fiddle around with all kinds of cells to find out mechanism of actions and say it's relevant for rats, it's not relevant for humans, or the other way around. But eventually, it's the public which really wants to know, is there a danger for me? Yes or no, of course. And this is a very thin line between trying to accept as the public that there is not a risk because that particular person's or that particular government says, we don't think there's a risk. And if you're a government, you're always one step behind because the public is they have a lot of distrust. And on the other hand, you've got toxiphobia. Which is part of the title. And the toxiphobia is actually meaning that people are scared for everything. Well, I'll tell you in advance, don't be scared for everything. By the way, if you want to ask me a clarifying question, don't hesitate to do so, okay? That's not a problem, but please wait with the discussions until I'm done. That's probably better. First of all, and that's what I already said, toxiphobia. It's really important to realize that over the last 40, 50 years, our detection limit of chemicals in the human body, in the environment, has decreased tremendously. Right now, we're at detection limits which are called femtograms, 10 to the minus 15 gram, and we can determine them in human blood, we can determine them in the environment. And if you put it in perspective, you've got a cell there and a nucleus in the cell. And a nucleus in the cell is about 1,000 times larger than a femtogram. So that's what we're really talking about. It's a tremendous achievement of the analytical chemist, but it's a very concerning aspect for the toxicologist when they try to explain that in this particular situation, there's no risk, although you may measure it. Measuring a little bit of PFAS in a polar bear doesn't necessarily mean that this polar bear has adverse health effects from the PFAS there. It does mean that PFAS has been distributed all over the world, and also in the Arctic and probably Antarctic regions, but that's a completely different issue. So the first toxicologist that's interesting. The first toxicologist is Paracelsus, and actually he made the first statement and he said basically that all substances are poisoned, there's none which is not a poison, the right dose differentiates the poison from the remedy. Say it shortly, the dose makes the poison. He also said it's the remedy, and that is something which has drifted away in our modern society, but at that time, when he was there in the 16th century, people were actually relying on botanical extracts for medication. And if you give too much from that botanical extract, you die. If you take a little bit of it, it may actually be beneficiary. For example, some medications for heart diseases are. So this was the first thing, and this was his conclusion, and it's still the major approach, the dose makes the poison for a toxicologist. In other words, he wants to know two things. First of all, is it poisonous? What does it do in humans? Secondly, how much is the exposure? And these two things together form the risk. And there's one thing he didn't know, and which I also advocate nowadays, is that there is a difference in, let's say, sensitivity between different life stages. And one of the things which I personally consider very important is the exposure in the early life stage, be it a fetus or be it a breastfed infant or a toddler between 1 and 3 years, which is definitely a more sensitive organism than an adult person. And that is right now inadequately incorporated in the risk assessment, and we could do better, but that takes a long time. So Paracelsus didn't know it. Unfortunately, fortunately, about 3-4 centuries later, we have enough scientific knowledge to say this is really true and should be an additional statement. So there are two things to remember. That's hazard and that's risk. If there would be a tiger walking here and there would be a gate like this between me and the tiger is a hazard, but there's no risk. If the tiger is able to walk on the stage, I think I'm at risk. That's a big difference. Don't let yourself be fooled by saying, if you hear from a Green Party, we saw 20 pesticides in apples and pears. Because the next question you should ask yourself, wow, are these levels high enough to do anything? The first thing is a hazard, because probably if you take 1 liter of that pesticide, you will die, but nobody does. And on the other hand, the exposure, the amount of exposure would say, this is actually a risk. And that's up to the toxicologist and the risk assessors to determine. Hazard, risk, completely different. And I think the tiger example is the easiest way to illustrate it from a popular point of view. The next thing a toxicologist wants to know is actually how does the dose-response relationship is actually determined, because dose-response means at some point you get an effect. And then it continues becoming worse and worse and worse in the population, humans, for example. And at some point it's saturated. As an example, dead. You can have a certain amount of pesticide in which only 10% of the population dies. You can have 20 times more, 100% dies. So meaning, I don't know, does this work? It's very small, but you can see. The most important aspect, and it's a very small point, I can say it just, the most important aspect for my dose-response relationships for a toxicologist is where the green arrow is. That's the position where a no effect goes into some effect. And you think, okay, clear enough. So if you know that, you can do risk assessment, everybody happy. The problem is that you have more things, and being at a technical university and looking at this graph, for example, you can imagine that the curve could be steep. In other words, it could go very fast to a very serious effect, but it also could go very slow, and it's a slope which is much less steep. But with an increasing dose, my most important aspect is the threshold here. That's where do I find the difference between no effect versus the first effect. And that can give toxicologists and risk assessors headache. Because it sounds so good, but in reality, how it went in the old days, I was sitting behind my desk with a compound which we had to study, and with a kind of educational guess, I had to determine different dose groups in animals. But I'm human. I can make mistakes. Let's say, interpretation could not be completely right, meaning that this particular point here, no, you cannot see it, so I walk over there. This particular point here looks very nice, because it's very close to the point where you have almost no effect to some effect. But if I would have made behind my computer a calculation mistake, or not even a mistake, but an interpretation, which is different, and that point should be up here, it's much more difficult for me to determine where my threshold is. So by now, we're all working with a completely different approach, which is called benchmark dosing. And from a statistical point, you can make an ideal sigmoid curve. But if I have a group of rats, and yes, unfortunately, we still have to work with animals. I don't like it, and we bring it down and down more and more over the last decades, but we still have to do it in some situations. But if I have a group of 5 or 7 rats, not all the rats respond the same. So I got a standard deviation in each group, meaning I got a sensitive rat in that group and a less sensitive in that group. So altogether, you come up with 3 lines. You come up with a line which is dotted here, which is actually the most sensitive, and on the other hand, you could have one here, and the least sensitive group. And when you apply these statistics, you can say, now I have the graph, I determined the sigmoid relationship, and I say, now let's say that at the 5%, that's where I have my threshold. And that's not so strange, because if you're doing your experiments, you also use p smaller than p is 0.05, 5%. So we do exactly the same, but now we have a completely balanced statistical approach. And then we say, by definition, there's the threshold between a low effect and a no effect. There's one exception, and that's cancer. And actually not cancer which is caused by cells who are suddenly completely changed because of situations in the metabolism. But we have quite a few chemicals which are working directly on the DNA. And when they react on the DNA, they disturb the interactions which are necessary. DNA translation through microRNA into proteins, into cellular responses. And those can be toxic. If a chemical binds to the DNA and does that particular effect, we use a different approach. Because theoretically, you could argue that one molecule, which I swallow, gets into my in my intestines, goes all the way into my body by blood, enters a cell, enters into the cell, goes into the nucleus, and binds to the DNA, and causes a disturbance there, which we call genotoxicity. And if it is doing it at the wrong positions of the database, the wrong basis, it may cause cancer. In this particular situation, theoretically you could say, one molecule could do the job. It's a single hit. From a practical point of view, it's probably not correct, because cells can repair itself. They can repair DNA damage, and if the cell can't repair the DNA damage, and your cells, my cells, animal cells, all over the world, they can kill the cell at the moment in which it's not working anymore, the repair systems. It's called apoptosis. So we have all kinds of defense systems, meaning that the single hit theory is probably a kind of worst case scenario. But what you do here, and sometimes you hear that, they say, okay, RIVM did calculate that 1 out of 50,000 or 100,000 people may get cancer at that particular exposure. And that's different from what I said earlier. There is a threshold level, a no effect, a lowest effect. But in that particular situation, because it acts on the DNA, and the single hit model for the toxicologists say it could cause cancer, one molecule. Worst case scenario, if I calculate it, and it's basically the dotted line going back to 0 from the dose response curve, instead of the slope. And we say 1 out of 100,000 people may get cancer. And from a regulatory perspective, it's accepted to say that if you're exposed to a certain chemical, which we can't avoid, and that may be cooking, for example, smoking. Well, smoking is a bad example with respect to the number of, let's say, cancer. But in food, on a daily basis, you're exposed to thousands and thousands of chemicals, which are actually causing DNA damage. Luckily for us, the whole repair system works perfect. So we're repaired continuously. Two problems: if you're young, the repair systems have to still be optimized. If you're old, you're going down the hill, and your repair systems are less effective. That's why cancer is, in fact, an old people's disease, because the repair systems don't work anymore that good. But most of you here, if I can see it well, are well in the age that you're still in a very healthy position, that your cells are clearly responding in a proper way against chemical attacks on the DNA, possibly causing cancer. And RIVM would calculate, okay, 1 out of 100,000 people, we feel it's still acceptable from a social perspective. It sounds, yeah, you can argue, oh, well, what if I'm the 1 out of 100,000? But that's in general what governments accept, 1 out of 100,000. Next question for a toxicologist in the whole risk assessment procedure is, if I've done my rat studies, are rats humans? Now, I can make all kinds of little jokes, yes and no, to say if rats are humans or not, but the reality is that the physiology of a rat is different than from man. So we have to incorporate those uncertainties, and the uncertainty factors here are mentioned, and of course I can't show the dot, but that's on the left side between rats to humans, divided in two things: how the cell responds on a chemical, and how the body distributes the chemical to different organs, to different cell types. And we build in as a default a safety factor 10. The next step is, and you understand that now, that if you have different age groups, you may also have different responses. And the different responses, and that's the families on the right, old people, young people, adult people, need extra safety factors too. By default, a factor 10. Depending on the situation, the toxicologist and the risk assessor may say, okay, I don't like 10 times 10 is 100 safety factor, but I'll put another 5, 4, and there is a mechanistic reason for it, for example. And then you bring in a safety factor 500. I can't say when we do this or that, but it depends on the compound you're studying and all the knowledge you have. So these are the 3 groups which are most sensitive in the human population. You don't have to read it all. Pregnant women, because the fetus is developing and has very little repair systems, if I may say it like this, including elimination, metabolism. Children, up to, you tell me, I really don't know. In general, they think it's somewhere between 1 and 10, but some toxicologists argue and endocrinologists say, I would go up to 15, 20, until puberty is gone. And some people never grow up, so maybe they remain sensitive. And then you got old people there, which I just explained, which are having less defense systems. Then eventually, before I get to some examples, some of the abbreviations which you may hear on the television or in some newspapers, like ADI, MRL, and acute reference dose. First of all, the acceptable daily intake. If you hear that the NVWA decided that a particular chemical or product should be taken off the market because the ADI is, let's say, you have a higher exposure than the ADI, and the ADI is nothing else than so much milligram, microgram per kilogram per body weight per day. And it's a lifetime exposure, what is included, because that's the worst scenario. So if you hear that NVWA said, I take this off the market because there is an increase in exposure above the ADI, the acceptable daily intake, you don't want to have that. You don't want to have that for a lifetime experience, a lifetime exposure. On the other hand, there is no need to immediately panic. Why not? Because first of all, this acceptable daily intake was based on lifetime exposure. Secondly, you have all kinds of repair systems. If you have an incidental higher exposure, which probably will take care of it if you are an adult in a healthy situation. Thirdly, you have the safety factors, 10 times 10. Because usually these data are derived from rodent experiments, sometimes dogs. Monkeys, luckily, we don't use anymore. Okay, so don't panic if you have a single exposure above the ADI and think, oh boy, now I get cancer. Forget it. It's not true. I don't know any examples in which this would happen. Maximum residue limit is actually what you get in through strawberries. Based on what you know acceptable daily intake, what you should not, let's say, you should not be exposed to a higher level than that. The maximum residue limit is how much should be in strawberries and how much should be in the spinach, Brussels sprouts, pig meat, etc., etc. And this is a kind of overall model in which they determine for different parts of the European Union or the United States what the diet is. And of course, some people like more strawberries than others, but that has been accounted for. Because again, you have the statistics, a 95% worst case scenario. So here we look at people which really like strawberries or Brussels sprouts. Me not. Okay, so last thing, acute reference dose, because we have to realize that at some situations, you're exposed to a relatively high level, and it may be dangerous. And that's the acute reference dose. And the clearest example I can give you is a farmer who is spraying unprotected pesticides, but he only does it 2 or 3 times a year. And then we have other toxicological studies indicating what type of risks are involved with that. And it's not chronic lifelong exposure like with ADI. Okay, now 2 examples. PFAS. Well, I guess most of the people which are here are well aware of the word PFAS, and they probably heard more about it. It's not good news. That's the bottom line. And the press and all kinds of green movements, well, it's justified. They made a lot of trouble about this and said we should take more restrictions on the use of PFAS. Personally, I'm involved with a very big project of the World Health Organization, and I'm chairing actually that effort for the next 2 years between the World Health Organization and the Food and Agriculture Organization in Rome, Geneva, Rome. And we're trying to figure out what actually the risk, how the risk should be determined of these compounds on a global scale. Because you have to realize that there is a big discrepancy in risk assessment often between, on the one hand, the United States, EPA, FDA, and on the other hand, the European Union. And this is originating from the fact that they look a little bit different at scientific publications. But you can have the strange situation that, for example, some fish species which are acceptable to eat in Europe are forbidden to eat in the United States because the ADI is lower in the United States than in Europe, or the other way around. That doesn't mean that the US is always actually more strict and lower in their safe levels, ADIs. In fact, the US is usually a little bit higher. So, PFAS, a lot of discussions about this. And what is PFAS? On the top, there are the two most common PFAS, and they're actually legacy compounds. They've been made at the end of the 90s, produced a lot, and we all use them. And if you look what makes these compounds so strange, look, in the past, we were actually just working with compounds like DDT, dioxins, PCBs. They were very bad water soluble, but PFAS compounds are water soluble. And besides water soluble, they can accumulate in the body. Why? For two reasons. If you look at the left side of the molecules, it's a non-polar chain, carbon, etc. On the right side of the molecule, in this particular situation, you have hydrogens and oxygens, or sulfur and hydrogens. It's polar. And because of these peculiar properties, they accumulate in the body, but are also well distributed through the water, ending up in the drinking water too. So accumulation and intake and exposure of these compounds come from two sides. With dioxins, PCBs, etc., we were always concerned about, let's say, dairy products, food, lipid-like fish chemicals, in which these chemicals were easily solved. The PFAS compounds also come in through the drinking water, and they have to be taken out. So it comes from two sides. And what they do, I'll tell you later. So PFAS is an extremely complicated situation, and this is actually to give you a rough idea how they circulate in the environment, how they end up in the body. And there are a number of effects mentioned which they can do. And let me tell you on forehand that these levels, these effects are not seen at all levels. Some of them are only seen at very high levels and others at low levels. And in general, we're still exposed to relatively low levels of PFAS, being human beings, but with fish, for example, it's different. So it's and we call it a One Health problem because we use it, we have it on our coats, we have it in our kitchen, etc., etc. But eventually, because of the carbon-fluorine bond, it's not easily broken down. It's only broken down high in the atmosphere, where you have enough UV radiation. And it's almost carbon-fluorine bond. We don't have any effective enzymes in our body to cut off the fluorine from that particular left tail, making them still PFAS. Where do we get it? Well, I always think the nicest example is this particular pan, cooking pan. PFAS has been used a lot to make cooking pans so you don't overcook your food. And the intriguing aspect is that this cooking pan doesn't have any problems for your health. Because the perfluorinated compounds, if you have two PFAS compounds, in the process they connect together, making a polymer. And it's actually the polymer, which you call Teflon, which is causing food, for example, not to become black. Because, well, a toxicologist always sees problems. But if you have black food, you have polyaromatic hydrocarbons, which are carcinogenic, even working on the DNA. So too much of those compounds isn't good either. So it's a bit of a balance, you know, risk-benefit. But on the other hand, during the production of Teflon, you got these PFAS compounds also released into the environment. And for the Netherlands, the clearest example is obvious, Dordrecht Chemours. And some of the chemicals which are in there have been taken off the market because they've been now assigned by the World Health Organization as persistent and compounds of serious concern. But industry is already making a lot of new ones. And this is just a little tree showing you, and almost daily there are new PFAS compounds produced. And the worrying part here is that to produce these compounds, very little toxicological tests have to be done. They can incorporate it in equipment without doing any toxicological studies. And this is how it works. That's the economical situation. But it gives a lot of uncertainties. If you look at the European Food and Safety Authority, they made extensive studies how all these PFAS are now in the blood of children and in the blood of adults. The two major ones, PFOS and PFOA, red and blue, we call the legacy because they're still around from 20, 30 years ago up to production 10 years ago. And you got a lot of new ones which are under there. And this gives a toxicologist a headache. Because what I'm actually seeing here is a mixture. And one of the things which is really, really difficult for a toxicologist is how to determine the risk of a mixture of chemicals. We can always do it for a single chemical. We do all the animal tests, all the cell tests. We determine if it works on DNA, etc., etc. But having a mixture of these PFAS compounds present in the blood, present in fish, present in milk, present in fruit, vegetables, we need to do some risk assessments on the total PFAS toxicity. And actually, I put a wallet there because how would you do that? Well, the normal procedure for a toxicologist is that they determine the relative potencies of each individual compound, in which they assume that the whole toxicity is additive. So you can compare that best if you have a wallet with 3 different currencies in there. They all have a different exchange rate. And we want to know how much euro you got there, while you have maybe Canadian dollars, the Japanese currency, and the Chinese currency. But there are converting values which you call exchange. And we have to do the same thing for these complex mixtures, but then for chemicals. And it will end up with one figure, which we compare with a reference compound. It's a lot of work, and if industry keeps bringing up new compounds, it automatically means that we have to keep working to find these conversion values for the new chemicals, because we're never exposed to only one PFAS compound. We're exposed to, rough estimates, the baby is exposed to about 30 to 35 different PFAS compounds, from which, as a toxicologist, I think that at least 10 are toxicological relevant. So you have to make the calculations. How much is actually a threshold there? The next thing with PFAS, you have to ask yourself, all right, I got all these worrying information about that they're very toxic. But if you remember that slide with rats, adults, families, I make a conversion from animals to humans. And within WHO, actually, my specialty is trying to understand if a mechanism of action in rats, mice, dogs, is really relevant for humans. And if so, for which age groups? It's a kind of, I wouldn't call it a hobby, but it's more a kind of specialism. If you want to look at that, the first thing you have to ask yourself, are the animal studies for PFAS representative for the human situation? And the right figure actually gives it, and this is from the Centers of Disease Control. They made a very nice one, it's called ATSDR here. The dark blocks are animal studies, and the light blue ones are human studies. So, for me, this is good news, because what I see here is that apparently animals respond rather similar to humans. In other words, I can rely for risk assessment on animal studies too. To some extent, because one of the things which keeps popping up in the news and in the media is that they're carcinogenic. And the carcinogenesis is on Leydig cells, some cells in your testes, the pancreas, and the liver. And to tell you the truth, as a toxicologist, I think the mechanism behind it is more rat-specific. So humans don't worry too much about cancer. We should be worried about other effects, especially immunological and liver hepatic effects. Those seem to be much more important from a human perspective. Especially the immunology is an important aspect, because why? It actually influences the youngest generations. And what they found was, and let's see if I can have the little point here. No, sorry, it doesn't work. Okay, I go over here. If you give a vaccination to a children's disease, diphtheria, mumps, measles, whatever you want to do, and you correlate that and the amount of PFAS, in this case it was PFOA, but there were also other ones, and you look at how effective that vaccination actually is to protect children against a children's disease, you see that if there would be no effect, it would be zero. But a lot of these effects from quite a few studies indicate that the response on the children's disease vaccination go to the left, meaning it's a response 5 to 35% less effective on the vaccination. That's serious business, because that means that your young populations are more prone to get children's diseases with all the nasty effects afterwards, maybe. And based on all the information we have here, we think that immunology in humans for PFAS is a serious one. That's the one we should look at. And so both EFSA as well as EPA, FDA in the United States looked at it and made calculations based on the levels which were in these children and the reduction in immune responses on vaccination. And they concluded that if you look what is still acceptable, the daily intake of PFAS, and that could be total PFAS with the currency exchange, is less than 1 nanogram per kilogram body weight per day. Children are exposed already to more than that. You can also say it's on a weekly basis, or for example on a group, and then you end up with 4 nanogram per day. Nanogram per day is 10 to the minus 9, a billion gram. It's very little, and we have sufficient evidence from Europe as well as North America as well as China and Japan that our present levels are significantly above that, children included. Pesticides, the other practical example. Worry or not to worry, you hear a lot. I've been involved with court cases for people living around bulb fields. If the children living there and are exposed to higher levels of pesticide should be at risk or not, should we have the precautionary principle, etc., etc., etc. Well, in May there is a new high appeal of one of these fields, and they want to stop because there are all kinds of houses around it. And the Netherlands are very much a tulip and a lily producing country. So this is a situation from which you can ask, if you build a small residential area around a bulb field, is that really something you like? Okay, first to the consumer. If you look at the consumer, sometimes you hear that blueberries, there's something wrong with the blueberries. There's a pesticide maybe in there, which is not good to get at your lifelong exposure, single exposure. My conclusion is that for consumers, adult consumers, if it's not a chronic exposure situation, you shouldn't worry. Where do you get most exceedances from pesticide levels in your food? From outside the EU. This is actually illustrated here. Brazil, Colombia, Dominican Republic, Egypt, India, Suriname, Thailand, and Vietnam. If you put this on a total perspective on what you daily eat, you're around 1 to 3% risk that you get something from those outside EU countries, which is a little bit elevated. And assuming you don't eat it your whole life, but it's just a single exposure or maybe a next exposure 3 months later, don't worry too much. Because you get safety factors, etc. So Europe has it well organized. This is, by the way, in Dutch, sorry, I only have a Dutch version from this one. Risk is in chronic exceedance, vulnerable groups, pregnant women, etc., and toddlers, we should be more careful with. Tonight is, I think it's the third time, the Keuringsdienst van Waarde sends out a documentary over baby food. I'm appearing in that one too, because what I actually said there was, the baby food is very well taken care of. Compared with what you eat, what you get from the grocery store, baby food is 100 to 1,000 times less contaminated with pesticides. So if you're a mother or a father, and you are actually think, well, I don't want to give the baby all the time baby food. I just go to the grocery shop and get some strawberries, etc., etc. Suddenly it doesn't count anymore. And you give the baby levels which are 100 to 1,000 times higher. Ridiculous. This is if you have, on the one hand, a very strict regulation for baby food, and then suddenly, if you decide to give the child healthy food, at least you think it's healthy. That doesn't mean baby food is that bad. But suddenly, these rules don't apply anymore. To my opinion, this is sheer stupidity of governments. Because when they assigned these strict regulations on baby food, as far as I can figure it out now, they basically forgot the pregnant women and the children between 1 and 3 which get healthy, fresh food. And they just forgot it, that they should make regulations for that too. Unbelievable, but it seems to be true. If you're interested, look at it tonight again. It's an interesting documentary to see how it works, and also how it works within governments and how they can fail. Okay, I think this is, yeah. If you look at pesticides, biocidal products, there's one thing I think you should say here, and that is, personally, I don't think that biocides are always bad. We took out a lot of biocides in the risk assessment, for example, which were acting on DNA and causing cancer, which turned out to be 10, 20 years later. We make now very strict regulations for hormone disturbances. And if a company brings up a new chemical as a pesticide, there's a big expansion of the tests. But two things they haven't done yet, and that is a test for Parkinson and a test for neurodevelopmental effects in the early life stage. And it's still not incorporated in risk assessment processes from EFSA, from EPA. Why? You can bring up all arguments, but for me, personally, I think the only reason they don't do it is for socioeconomic factors. Because it means actually that it takes longer to bring a product on the market. In other words, earning money, shareholders. In this particular situation, in the Netherlands, we also have to realize that we have a luxury. It's very luxurious to think about, let's eat biological only. A lot of people, and I assume a lot of people I see here, can afford to buy biological food and eat it. Is it needed for adults? From a pesticide point of view, probably not. Because I don't think your life expectancy and you have a higher incidence, you don't have a higher incidence from the daily exposure to pesticides if they're below the acceptable daily intake. It may be different for children and pregnant women. I don't know. Should we take the precautionary principle? I don't know. In this particular case, we just didn't do the test, so I can tell you yes, I can tell you no. And then, if you eat biological food, there's one thing, and that is really important, you save ecological problems. Because not using too many pesticides in a small country like ours means also that the impact on the ecosystem will be much less. And there is definitely collateral damage from the use of pesticides by the present agricultural, let's say, situation on the ecosystem. So if you ask the toxicologist Martin van den Berg, do you think it's dangerous for me to eat normal fruit and vegetables, which are at the normal levels? I don't think so. If you ask Martin van den Berg without being the toxicologist, I would say, I would prefer biological food, use as less pesticides as possible to bring at least our sensitive ecosystem in this very small country with a lot of agricultural activities to a better situation. That's what I would say as a person, but not as a toxicologist. Diseases. Let me check. I'll see it. Something about diseases. Two diseases are very prominent. Parkinson, and I guess you may have heard about it. Parkinson is definitely, it's a neurodegenerative disease. It destroys some cells in parts of your brain. That causes Parkinson. We know that certain pesticides can do that. And we also know that especially farmers are more at risk than you and I when we go to the grocery shop, honestly. So that's another thing. And here you see, for example, the epidemiological studies indicating this is 100% increase. And the little blue boxes are the averages, and I don't think you can deny that they all move to the right, and you do see an increase of 50 to 100% Parkinson for people working in agricultural sections. But they are exposed to higher dose levels. That's not only for Parkinson, but it's also Alzheimer's disease, similar but less studies, and autism, ALS, etc. Studies are less than with Parkinson, but there are links there. There are signals which causes a neurotoxicologist to worry. Finally, there are two different things. Neurotoxicology can go two ways with mixtures of pesticides. It could go neurodegeneration, Parkinson, and it could cause the neurodevelopmental aspects. And the neurodevelopmental aspect is actually how the brain parts develop. That relates to exposure to children, which are less concentration, hyperactivity, autism. Some of them are stronger linked than others. And I don't take position here that all chemicals, all pesticides are doing it. But what I take position against is that we still don't use the right toxicological studies to regulate these compounds, because EFSA isn't still incorporated as obligatory for industry to do so. And that's important to know. And I think with that, here's a quick list. I want to give you take-home messages which are really important from a toxicological point of view, besides PFAS and the pesticides. First of all, the dose makes the poison. Think about that when you hear something again, that there's something wrong with something. Hazard is no risk. Think about that tiger there, which is a clear difference. And finally, the timing of the dose, and that's important for PFAS as well as for pesticides, is important. And we do not test it enough. And those are, I think, the main take-home messages for you. Thank you.